Hello everybody, welcome to the second lecture on chemical kinetics. Before I go ahead with the lecture this time, what I will do is I will quickly do a recap of what we did in the previous lecture, at least some part of it, because I am going to continue with certain aspects which I did not discuss last time in detail. So, if you would remember and if you would look at this PowerPoint slide, we were talking about the introduction for chemical kinetics, and we were discussing that thermodynamics does not give you everything. It tells you that the reaction or whatever you are looking at, the process is supposed to happen, but it does not tell you or give you any time information, and that is why kinetics becomes or plays a very major and important role in chemistry. And in doing that, we started discussing some examples, very relevant examples, and one of the examples, if you remember, we took up was with regards to the catalytic converter present in a car. And as you can see, if you would try to recall what we had in previous lecture. So, this slide is showing you a catalytic converter. You have, so the first slab has rhodium as a catalyst as written out here, then the second slab has platinum, palladium as catalysts. So, the first this slab, if you follow my white pointer, it helps in reducing the oxides of nitrogen to nitrogen itself, and the second one makes sure that it oxidizes the carbon monoxide and hydrocarbons which were not burnt to carbon dioxide and water which are not harmful. Now, while doing that, and if I go forward, so this is essentially what we are looking at. So, it says what how a catalytic converter works, and we were discussing at length about the reactions involved, the catalysts, what they do and all. In doing so, what we had mentioned also was this photochemical smog. We had said that if we do not have a catalytic converter, then the emissions coming out, which are the oxides of nitrogen, carbon monoxide, unburnt hydrocarbons, then they start polluting the atmosphere, giving rise to air pollution as we know. Now, we also said that this photochemical smog is a typical feature where the pollution is not controlled. We have a huge number of automobiles plying each and every day. Then I also told you, if you remember at the time, that we will come back to this word photochemical later, why it is called photochemical, but in that lecture we do not have the time. So, what I will do is I will in continuation with that lecture and what we had discussed, I will spend some time on this photochemical smog issue and then move further on with chemical kinetics. So, with regards to the photochemical smog, and as you would realize, the word photochemical, if you talk about this word photochemical, and if you split it up, it will split up into two things. Photo means coming from photons, which is light, and then chemical. We are talking about a chemical process or a chemical reaction, which means that when we say photochemical smog, we are talking about a reaction or a set of reactions which is induced by light or photons. Okay. Now, typically when you look at this smog, this photochemical smog, it has a brownish tinge or haze. Then the question is, where does this color come from? So, let us look at that. This color in the smog comes from a key ingredient in the smog, a key ingredient in the smog, and that key ingredient is nitrogen dioxide. So, nitrogen dioxide, it absorbs visible light. It absorbs visible light, light we can see, we can visualize. So, on absorbing, what happens is, if I have NO2 out here, which we are talking about, then I represent the photons as h nu, where h is the Planck's constant, nu is the frequency, you all know about it. Then for a frequency of about 400 nanometer or less, if NO2 molecules are being hit by light of this wavelength or lesser, that means 4 nanometer or lesser, then what we end up getting in terms of the reaction is NO plus O. Okay. Let this be our reaction 1. So, we are getting nitric oxide plus oxygen. Now, the oxygen atoms obviously are very reactive. So, what will happen is the oxygen atoms react immediately. So, O3 plus O. So, oxygen atoms react immediately with, just make this correction, this is oxygen of the atmosphere O2. So, O2 plus O will be giving rise to O3, ozone, and you know that this ozone is being produced out here from the oxygen atom, which was coming from the splitting of nitrogen dioxide into NO and O photochemically, and this oxygen or this oxygen atom combines with O2 to give us ozone, right. Now, remember we had talked about incomplete combustion also. So, incomplete combustion means that we have some unburnt hydrocarbons. So, when we have unburnt hydrocarbons, if you represent it as the unburnt hydrocarbons as RH, then what we can say is happening is that RH can react with this hydroxyl radical. I will tell you where this hydroxyl radical is coming from, to give R dot plus H2O. So, let this be equation 3 and this becomes equation 2. So, so here you see we have the production of ozone, right. Then we have this incomplete combustion, because of which we have these hydrocarbons which were not burnt, which passed through to the atmosphere, and this RH then combines with or reacts with the hydroxyl radicals in the atmosphere to give rise to this R dot radical plus H2O. Now, what happens to this R dot? So, R dot now goes ahead and reacts with the oxygen of the atmosphere to give rise to ROO dot. Now, this ROO dot, let this be reaction or equation 4. Now, ROO dot you immediately realize is a peroxy radical. Like hydrogen peroxide, we have this O peroxy bond. So, this is a peroxy radical. Now, in this peroxy radical, the OO bond is not that strong. So, the OO bond in ROO dot is weak in nature. So, then what would happen is this weakened O bond can readily donate an oxygen atom. So, like this. So, I can have ROO dot, right. It then reacts with NO to give me, so it is donating an oxygen atom now to give me RO dot plus then NO2. Okay. So, let this be equation 5. So, see where we started from, what the splitting of NO2 to NO and O. This O reacted with oxygen to give me ozone. Then we went on to unburnt hydrocarbons represented by RH, which reacts with hydroxyl radicals. If you remember, RH plus OH dot gives you R dot plus H2O. Now, this radical, this hydrocarbon radical now reacts with oxygen of the atmosphere to give us a peroxy radical ROO dot. This peroxy radical has a weak OO bond, hence this bond can be easily broken. So, the peroxy radical, what it does is it donates an oxygen atom to NO via this reaction, giving rise to RO dot plus NO2. What other reactions can take place? So, again keeping in mind the fact that this this hydrocarbon having reacted with OH dot, you must be wondering where this OH dot is coming from. So, let us see that. So, the OH dot comes from this equation. So, now what we are trying to look at is how do the OH radicals come about or come into existence. So, here remember there is ozone which we had looked at, right. So, ozone, so it is oxygen combining with O coming from NO2 to give you ozone. See, ozone in presence of light, again photons, less than say 325 nanometers. So, photons having wavelength of 325 nanometer or less, when they fall on ozone, this is what happens, you get oxygen plus O star. So, let this be equation 6. What is O star? So, O star, so star means excited state. So, all of you must be knowing that you have ground states, excited states and so on. So, this O star represents the oxygen atom in the excited state. Now, it goes without saying that because it is in the excited state, it is having a lot of energy, and at the first available opportunity it will try to get rid of this energy. That means, it will try to react with something. How does it do it, or what reaction does happen after this? So, what happens now is, because you have water vapor in the atmosphere, this O star now reacts with water to give you 2 OH radicals. Let this be equation 7. Hopefully, now you will realize why in case of that hydrocarbon reaction RH, the unspent or unburned hydrocarbons which reacted with OH dot to give you the corresponding radical, right, RO dot, So, this R plus OH dot, when you got that, the reaction I am talking about is, if you remember, the reaction I am talking about is this RH plus OH dot giving R dot plus H2O. So, when we said that this OH dot, how do we get this OH dot? This OH dot is available or coming to us like this. Now, what happens to this OH dot also is that we have NO2. So, there is another reaction plus OH dot gives you HNO3. You realize now that this is nitric acid, hence the term acid rain. NO2 plus OH dot, which we saw just getting produced from this excited oxygen atom, which was obtained from the splitting of ozone, right. And just one thing I forgot to mention, when you are talking about the splitting of ozone, you see this wavelength of, if I say this wavelength of 325 nanometers, if you consider this wavelength of 325 nanometers, right, this we refer to as the harmful UV or ultraviolet rays. So, this is in relation to your ozone holes. That means, if you have harmful ultraviolet rays, and these ultraviolet rays, what they do is they split ozone up into molecular oxygen and excited oxygen atom, which then goes on to show the other reactions. Now, that is why the reason we had all this discussion was to make the point that these reactions would be occurring to a large extent, giving rise to air pollution, if we do not take care of the combustions in this case coming out from the cars, and we have so many cars on the roads nowadays that if emission standards are not met, then the pollution level will go up dramatically, right. So, hence I think that I have been able to make the point about why we were discussing that the need for all these equations. These are this is more on the environmental chemistry side rather than just to do with kinetics, but it is extremely important to know why the catalytic converter has to be there, what are the reactions involved, what are the catalysts involved. Catalyst definitely is a part of chemical reaction, it enhances or it increases the rate of reaction by decreasing the energy barrier, which we will see later, right. So, that is why catalysts are there, they make sure that most of the harmful gases are converted into those that are less harmful or not harmful at all. Some gases do escape because maybe the combustion or the conversion is not 100%, and those would go and give rise to air pollution, like all the equations we have written out here culminating in this acid rain. So, it is extremely important that we know this and we relate it to the need for having a cleaner, better air. Okay. Now, let us move on. So, we have talked about we have talked enough of the introduction. So, where did this all began, but before going into this chemical kinetics about the rates and all, let us talk about this. So, you might come across something referred to as thermodynamically unstable, but kinetically stable. Let us take an example to see what this means. So, let us go to this slide. On this slide, what you are seeing is the hydrolysis of ATP, adenosine triphosphate. Now, you can see this adenosine triphosphate, this is the structure of adenosine triphosphate. It is having 4 negative charges, right, triphosphate. So, 3 phosphate groups, if you follow my arrow, 1, 2, 3 phosphorus atoms, and the rest are the oxygen atoms along with the phosphorus. Now, what happens is hydrolysis of ATP releases a lot of energy. So, if you see, if you look at this slide again, what you are seeing is that you have adenosine triphosphate and hydrolysis, that means on reacting with the water, which we call hydrolysis, will give rise to adenosine diphosphate. In adenosine diphosphate, what has happened is one of the phosphate groups has been hydrolyzed off, or it has snapped out, that means it was broken off, it has come out. So, you get adenosine diphosphate. Adenosine diphosphate now has 3 negative charges instead of 4 as was there in adenosine triphosphate, and now this adenosine diphosphate having the 3 negative charges, along with that we have this phosphate, inorganic phosphate, which has come out, and H plus. Okay. Now, if you have to write this in equation form, the way you will write is, so as I say, we were discussing the hydrolysis of ATP, right, and in this hydrolysis of ATP, what you are saying is that I have ATP, there are 4 negative charges. So, 4 minus plus H2O, we are looking at the hydrolysis of ATP, right, having 4 negative charges. It gives me ADP, adenosine diphosphate, from tri to di, I have lost 1 phosphate group, this has 3 negative charges, okay, plus HPO4 2 minus plus H plus, right. This hydrolysis comes with release of energy, right, and in this case, as you can see out here, if you go back to this slide again, you will see that the conversion of ATP to ADP as illustrated yields about 7.3 kilocalories per mole of ATP. This much of energy is released when we go from ATP to ADP, right. So, often if you are talking about the thermodynamic feasibility of a reaction, you talk in terms of change in free energy, right, change in free energy which is delta G, and in this case the change in free energy is equal to is almost equal to minus 30.5 kilojoules per mole. So, that means the change in free energy delta G in this case for the hydrolysis of ATP to ADP is highly negative, that means it is highly spontaneous. That is why, because it is spontaneous, that is why it is often ATP is referred to as the energy currency of the cell or body. Okay. ATP is often referred to as the energy currency because it provides energy. Now, the thing is, if it is thermodynamically feasible, it might make you think that it will always happen just like that, right. That means, our body will never be able to have ATP stored because it will immediately be converted to ADP, as it would seem from the thermodynamic feasibility of the reaction, because delta G is so negative. But you know what? So, this is called thermodynamically unstable, which means that the ATP is thermodynamically unstable, right. However, the point is that it can be thermodynamically unstable, but kinetically this reaction, this hydrolysis reaction, I can write the hydrolysis of ATP is very slow, right. Hence, we call it kinetically stable, which means that though it is thermodynamically very much prone to hydrolysis, but the rate of this hydrolysis is very slow. This is why, remember, when we started this section of our discussion, we said this there can be something which is referred to as thermodynamically unstable, but kinetically very stable, and the hydrolysis of ATP is an example of that. Which brings us to the very start of an introduction, that is the previous class, where we were saying that thermodynamic tells us only about the feasibility of a reaction. If it is negative, that means it is supposed to happen. If it is positive, that means if the free energy is positive, that means it is a non-spontaneous process. But what it does not tell us, even though say delta G is highly negative, as we saw in case of the hydrolysis of ATP, what it does not tell us is the rate at which this reaction, in this case hydrolysis of ATP, is supposed to happen. And as I told you right now, this being kinetically very slow, which means that though it is thermodynamically very feasible, kinetically it is going to take, or in terms of time, it is going to take a long time to take place. Hence, this reaction is called, or this process is called thermodynamically stable. I mean the hydrolysis of ATP, thermodynamically stable, or rather thermodynamically unstable, I am sorry, thermodynamically unstable, but kinetically very stable. Okay. So, that is why the need for kinetics and to understand what kinetics involves. Another example is, if you again here, another example has to deal with graphite and diamond. Graphite and diamond, what they are? Graphite and diamond, these are allotropes of carbon. Now, what it turns out is, graphite being more stable than diamond, what it means that since graphite is more stable than diamond, then this is, I would expect that if I have any diamond, that would spontaneously convert to graphite. Now, think about this, then all of us who would be having diamond rings or any diamond items, right, they should have immediately converted to graphite, right, but does it happen? No, it does not happen. Again, this is a case of thermodynamically unstable. So, I can write then diamond is thermodynamically unstable, right. It is thermodynamically unstable, but this reaction or this conversion is very slow. Hence, we say that this process is kinetically quite stable. Thus, you do not have to worry about this, that diamond getting converted to graphite. It takes a long time, which, so let me go up. If you look at the slide, you can see that at the bottom there is written this popular statement, diamonds are forever. They indeed are forever, because though diamond is not the most stable form, graphite is. Hence, in terms of the free energy of conversion, this process is spontaneous. Conversion from diamond to graphite has delta G negative, but because kinetically the reaction goes very slow, this reaction is referred to as kinetically being stable. Again, makes us come back to this point again. The thermodynamics only tells us about whether the reaction is going to happen or not. It does not tell us or give us any information about the time involved. Good. So, having made these points, let us now try to go into the kinetics, the formulations of kinetics and so on. Now, what we will start with is say the birth of chemical kinetics, Now, this goes back to as old as 1850, when a person called Ludwig Wilhelmi did something. What did he do? What he did was, he followed the breakdown of cane sugar. He followed the breakdown of cane sugar, or I can write sucrose, in acid solution into glucose and fructose. So, Ludwig Wilhelmi was observing a process which involves the breakdown of sucrose into glucose and fructose. Now, what did he find? This is what he found. What he found was that Wilhelmi noted that the reaction rate at any time, the reaction rate at any given time was proportional to the amount of sucrose left. So, again think about the implications. He is saying that after the reaction started, at the start of the reaction, during the progress of the reaction, the rate of the reaction at any time after the start of the reaction was always, I can say, directly proportional, according to him, directly proportional to the amount of sucrose left in the reaction mixture. That is the sucrose which was left unreacted. I can write left unreacted at that time. Hence, Wilhelmi is often referred to as the father of chemical kinetics, often referred to as the father of chemical kinetics because of this observation of his. This is or this was the birth of chemical kinetics as we know of it right now. Now, since then chemical kinetics has seen many levels or degrees of advancement, right, and to top it off, just to share this information with you before I go into the rates and all, up till now 9 Nobel prizes in chemistry. I am sure you know what the Nobel prizes are. 9 Nobel prizes in chemistry have been awarded to the field of chemical kinetics. Just wanted to share this information with you, so you understand how important this is, as a part of chemistry, and that is why we are here to discuss and talk about chemical kinetics. Okay. Now, again going back to chemical kinetics, what is it? Simply put, if you have a reaction, you would want to know how fast or how slow the reaction is going. That means, what you are dealing with? You are dealing with the rate of a chemical reaction. Okay, so, that means you are going to follow a reaction as a function of time. So, let us do that. So, say we are looking at rate of a chemical reaction. This is what we want to do, and when we do this, what does a kinetic study involve? A kinetic study, that means a study in chemical kinetics, involves following the rate of a given reaction, any reaction you are talking about or you are thinking about or you want to discuss, as a function of time, right. So, this is important. So, as a function of time, that is why it is called the rate of reaction. Okay, that is why it is called the rate of reaction. What is the time taken for that specific reaction to proceed in the direction which is supposed to go. Now, this can be done in a number of ways, right. There are many analytical techniques, like many analytical techniques exist by which we can measure changes in concentrations of reactants or products. Sorry, this would be, let me write this again, reactants or products or both together. No, it does not matter, because when your reaction proceeds, your reactants would slowly disappear and your products will slowly appear. Both are happening as a function of time, and depending upon the reaction you are considering, both would be following a certain rate, and you can have enough information about the rate of that chemical reaction by following either of these or one of these. Now, in terms of the analytical techniques, what I mean by that is, see, when you are saying that okay, this concentration is decreasing, this concentration is increasing, how do you realize that? How do you realize that? This realization or the way you follow the decrease in concentration of reactants or the increase in concentration of products is typically done through a range of techniques referred to as analytical techniques. The techniques involve, very simply speaking, you can monitor the pH of a reaction, right? You can monitor the pressure changes in a reaction. If your reaction is colored, that means you have color in the reaction, you can monitor how that color changes as a function of time. So, which means, so think about this. Suppose your reactants are not colored, but your product is colored. Then what you can do is, you can say that okay, I would look at the color and I would see how the intensity of that color is varying or changing as a function of time, right. So, this color change is done through spectroscopy, like absorption spectroscopy, or you can also say that okay, I have a reaction where my reactants are colored, but my products are not, are colorless, my products are colorless. Then what you would see is, you would see that you would start with a reaction which is quite intensely colored, and then with the progress of the reaction, as time increases, the color disappears and goes to colorless. So, again, if you would follow this color change as a function of time, you will be having an idea of the rate of the reaction. So, there are many ways. I just told gave you a few examples. So, the examples were like the pH change, right. You can consider pressure change, you can consider change in, sorry, this is change in color. All these can be used to follow reactions and determine reaction rates. Next, there is a very important point you have to keep in mind. When you do these measurements to figure out how the change is happening, so that it leads you to the rate of that chemical reaction, all these reactions, so this arrow is from the previous page, all these reactions need to be carried out under isothermal conditions. All these reactions need to be carried out under isothermal conditions. What does isothermal mean? Isothermal means constant temperature. This is extremely important. Why is this important? Because you know that the rates of reaction are dependent on temperature, right. You increase temperature, the rate of reaction will change. Hence, it is extremely important for you to make sure that the temperature is kept constant when you are measuring the rate of that reaction or performing the experiment on chemical kinetics. However, if your idea or if your goal is to measure the temperature dependence, is to measure the temperature dependence of the reaction, then it is obvious that the temperature needs to be filled. So, then what have we said? We have said some very simple, but very significant things. Say for the rate of the chemical reaction, when we said that when you do a kinetic study, it involves following the rate of a given reaction as a function of time. This is referred to as the rate of the reaction. How do you measure the rate of the reaction? So, the measurement of the rate of reaction is done by looking at changes in concentration or changes in concentration of reactants or changes in concentration of products or both. How do you measure these changes? You measure these changes by certain analytical techniques, some examples being say a pH change, you can do through say potentiometry, pressure change, if the reaction involves changes in color, then those changes, and so on. Not only that, because reaction rates are very much temperature dependent, it is extremely important that if your goal or focus is only to measure the reaction rate not as a function of temperature, but at a certain temperature, then it is essential that isothermal conditions are maintained. However, isothermal means constant temperature, that means the temperature does not vary, otherwise the rate of the reaction will vary and you will be having erroneous results which are not correct or accurate. However, it is obvious that if you really want to look at the temperature dependence of a reaction, then you have no other option but to allow the temperature to change. That means you change the temperature yourself and then you see that how the rate is varying. To clarify what I meant by allowing the temperature to vary is that I do the same reaction at different temperatures. So, what do I mean by that is, suppose I have this reaction A going to P, right. I want to see the temperature dependence of the reaction, and how do I do that? I say I start with an initial concentration of A, of the reactant A. Okay. Now, once I start with that, what I will do is I will run several experiments. That means the same experiment as a function of time, which is the kinetics, I will run. How will I run it? Suppose this is experiment 1 and this experiment 1 I run at temperature say T1, then I have say experiment 2 and I run at temperature T2 and so on. So, I have experiment 3 I run, which I run at temperature T3, again I have experiment 4 and I run it at the temperature T4. So, these are my temperatures. So, these are my temperatures, right, and what I am doing is I am running exactly the same reaction where I start with the same initial concentration of A. Okay, I do not change anything. I run the experiment multiple times, but what do I do is for each and every run, say experiment 1 which is run 1, the first time I am doing the experiment, say I am doing it at temperature T1, then I do the same experiment at temperature T2, again I do the same experiment which is say experiment 3 now, but this, remember, this is the same experiment. So, what I mean is that I am just going for different runs of the same experiment. Okay, I am not changing anything else, I am starting with the same initial concentration of A. The only thing I am changing is the corresponding temperature. So, that is experiment 1 or run 1 is done at temperature T1, experiment 2 is done at temperature T2, experiment 3 at T3, experiment 4 at T4 and so on. So, by this what we do have is we have the dependence of the rate of this reaction, which is A going to P, as a function of temperature, and this is what I meant when I said the temperature dependence of a reaction rate when it is supposed to be taken or when it is supposed to be measured. I have to vary the temperature. That means, I vary the temperature for different subsequent runs. The more the number of temperatures you have, the more the number of points you have, and it is better you for any subsequent analysis. But the take home point is that when I have to do the temperature dependence, or if I have to see the effect of temperature, I have to run the same experiment, okay, different times, say experiment 1, experiment 2, experiment 3, experiment 4. This is the same experiment I am running, this like different runs of the same experiment at different temperatures, say T1, T2, T3, T4, T5, T6 and so on, depending upon the number of points I am going to take. So, again this is what I meant by temperature dependence, and this has to be done if you are studying the temperature dependence of that reaction. Okay. So, these statements might look very straightforward, but these are for some very significant statements that you have to keep in mind before you embark on actually doing an experiment related to chemical kinetics. Okay. Now, let us consider a reaction. As I said that it is time we start going slowly into the realm of reactions and talk about rates and so on. So, let us take this following reaction. So, the reaction is a very simple reaction, ClO minus, this is a hypochlorite ion in aqueous medium, reacts with bromide ions in aqueous medium to give you BrO minus, that is hypobromite aqueous plus Cl minus aqueous medium. So, it is an aqueous phase reaction. So, this is your hypochlorite ion, and as we were discussing, we are going to say study the kinetics of this reaction at a fixed temperature of say 25 degrees Celsius or can say 298 Kelvin. So, again as I said, if you are not interested in looking at the temperature dependence, then you have to look at the reaction rate at a fixed temperature, isothermal conditions. Those isothermal conditions, in this case we say that the temperature is being fixed at 25 degrees Celsius or 298 Kelvin. So, that no temperature dependence is being brought into question. Okay. Let us just look at how the plot would look. So, this is called, or the one I am going to write now or draw now is typically referred to as a kinetic plot. So, let us see if we can do it well. So, these are my two axes. So, these are my two axes, x and y axis. So, in this axis I have time in seconds, right. Here on the y axis, you can write concentration, right, moles per liter, right. For this reaction, as I said, hypochlorite reacting with bromide giving you hypobromite and chloride. Okay. Now, first I will try to use different colors just to make sure that I can distinguish between the reactants and the products. Okay. So, first just let me draw this. This is not exactly drawn to scale, but hopefully it would be good enough or okay to give you the idea. Let this be for ClO minus, then I have Br minus, and I have I can write BrO minus and Cl minus. Say this is, if I try to write some numbers on the axis. So, this is the 0 of time, and then I will be having different times out. Okay. Now, realize one thing, when I am drawing these lines, there is a small problem. The problem is that they look continuous lines obviously, but when you do the experiments, you understand that you always measure at certain points, right. So, when you measure at certain points, what you will be having is, you will be having say an experimental point out here, right, an experimental point out here, an experimental point out here, experimental point out here, experimental point out here. And for my convenience, what I have done is, initially I drew the line and then I am putting the experimental points. I will discuss in detail in the next class about the significance of this, but what it means is, I have done the experiments at each and every point corresponding to this time, right, this one, this time, this one, this time, this one, this time, and then after having done the experiment, I am drawing a smooth line which is passing through these points. So, similarly I can put a point out here, I can put a point out here, for this one I can put a point out here, I can put a point out here, okay. For this one I can put a point out here, here, point out here, right. So, what are you seeing? What are you seeing out here is that this is the concentration on the y axis in moles per liter, on the x axis you have time in seconds. So, as you go along the x axis as a function of time, there are some changes in concentrations. What are the changes like? If you are talking about the reactants which are hypochlorite and bromide, at time 0, when the reaction had not yet started, it was just before the start of the reaction, the initial concentrations were given as here. For example, the initial concentration of Br minus was this point, the initial concentration of ClO minus was this point. Now, as time proceeds, because these are reactants, they are slowly lost, that means they are disappearing. Because they are disappearing, the concentration of Cl minus and the ClO minus and the concentration of Br minus in the blue lines, both of them are decreasing. On the other hand, if the reactants are decreasing, then obviously the products are appearing, that means the concentration of the products is going ahead or going up. So, if you look at the green line now, if you look at this green line, which corresponds to both BrO minus and Cl minus, what you see is, before the start of the reaction, there was no product out there, okay, 0 concentration of hypobromite, 0 concentration of chloride. But as the reaction progressed, that means as we progressed along the x axis as a function of time, the graph, that means the plot of BrO minus and Cl minus slowly went up from 0, which makes sense. Why? Because reactants are lost, but products appear, that means products are formed, the concentration of products increase as a function of time, and that is how this kinetic profile is looking as it should look, and it is often referred to as a kinetic reaction profile. So, again to end the class for today, the blue lines refer to those of the reactants. The blue lines, as you can see, the lines are coming, I mean the blue lines, they show a decrease as a function of time because the reactants are getting used up. The green line with the experimental points, which corresponds to whether BrO minus you are looking at, Cl minus we are looking at, this green line shows an increase from 0 in value. Why? Because the products are being formed, right. This is this plot, it can be for any reaction, but in this case we are considering a specific reaction, the reaction of ClO minus, that is, since we are talking about this reaction, hypochlorite plus bromide giving you hypobromide plus chloride. Hence, this plot is referred to as the kinetic reaction profile for the reaction we are talking about. So, what we will do is we will from here we will start the discussion in our next class. Okay. Thank you.